Show by the principle of mathematical induction the inequality given by 1 plus x whole raised to the power of n is greater than or equals to 1 plus nx whenever x is positive and n is a positive integer. Okay, let us begin. So first what we'll do, we're going to consider a statement and denoted by p of n. So let p of n be the statement which is given by p of n such that we have 1 plus x whole raised to the power of n is greater than or equals to 1 plus nx. We're going to call it statement number 1. So here x is a positive and n is a positive integer. So our goal will be to verify this statement. We do not have to prove the inequality. Our only goal will be to prove that through the principle of mathematical induction that this is a true statement. That means any value of n that we take, that means any integer, positive integer that we take, this statement must be always true. So first what we'll do, we're going to verify that if this is a true statement or not for n equals to 1. So for n equals to 1, first we will try to check the statement p of 1. All we have to do is replace n with 1. So we have 1 plus x raised to the power of 1 greater than or equals to 1 plus 1 multiplied to x. So that means we are getting 1 plus x greater than or equals to 1 plus x. And this is indeed a true statement. Since this is a true statement, here we can say that our statement p of 1, this is going to be a true statement. So p of 1 is true. But we'll also have to verify for other other integer values as well. So let us consider a statement p of n and assume it to be true. So let p of m be a true statement. Now what is p of m? Now p of m means we have the statement p of m such that 1 plus x whole raised to the power of, now we're going to replace n with m. This is going to be greater than or equals to 1 plus m times x. Now we have m, which is an integer. So let's call it statement number 2. So we are assuming that this is a true statement. And using this statement, we'll have to show that if we consider the consecutive integer m plus 1, p, which is going to give us the statement p of m plus 1, we'll have to show that this is also a true statement. So how do we show that this is a true statement? So before that, let's try to understand the statement p of m plus 1. So the p of m plus 1 must state that if we take 1 plus x and raise it to the power of m plus 1, we're replacing m with m plus 1. This must be greater than or equals to 1 plus m plus 1 whole multiplied to x. So we have to verify that this is a true statement. So to do this, let's call it statement number 3. Now, in order to verify statement number 3, we'll have to consider statement number 2 because 2 is a true statement. So from our statement number 2, so we'll consider the inequality, that is 1 plus x whole raised to the power of m. So this is going to be greater than or equals to 1 plus mx. This is a true statement. Next, what we'll do, since x is a positive value, here we know that x is positive. So x is positive. In other words, what we are saying here, that x is greater than 0. X being a positive number. And if we add 1 to both sides of the inequality, we get 1 plus x is greater than 1. In other words, what we are saying here, that 1 plus x is also positive. This is also positive in nature. So what we will do, we'll take 1 plus x and multiply to both sides of the inequality. And since 1 plus x is a positive number, that is not going to affect the sign of the inequality. So that means we have 1 plus x multiplied to 1 plus x raised to the power of m. So it's still going to stay as greater than or equals to 1 plus mx multiplied to 1 plus x. Fine. Now what is 1 plus x multiplied to 1 plus x raised to the power of x? It is simply 1 plus x whole raised to the power of m plus 1. So this is going to be greater than or equals to, we'll multiply both of them. That's going to give us 1 plus x added to mx added to mx squared. Fine, we're going to keep it aside for the time being. Now, since it's already given that x is positive, we can state here that since x is positive in nature, so we can say that x is going to be greater than 0. Then squaring it is also definitely going to make it greater than 0. And if we multiply m to both sides, we have m times x squared. That's going to be still greater than 0 because m here is also an integer. M belongs to the set of positive integer. So m times x squared is going to be greater than 0. Now, if m times x squared is greater than 0, then what we can do here? So here, we can say if we add 1 plus x plus mx to both sides. So we have 1 plus x plus mx plus mx squared. So that's going to be greater than 1 plus x plus m times x. All we're doing is adding these three terms to both sides of the inequality. So here 1x, mx, these are all three positive numbers. So it's not going to affect the sign. So here we are saying that 1 plus x plus mx squared, that's greater than 1 plus x plus mx. Now, if we combine, so let's call it statement number 3. And this is inequality or statement number 4. If we combine 3 and 4, then what we'll get, so let's combine them. We have 1 plus x whole raised to the power of m plus 1. So this is going to be greater than or equals to. Now, in place of 1 plus x plus mx squared, we can simply replace it with 1 plus x plus mx. Fine. Now, what is 1 plus x plus mx? We can simplify the expression on the right hand side. So on the left hand side, we have 1 plus x raised to the power of m plus 1. This is greater than or equals to 1 plus. So if we combine the second and the third term here, so that's simply m plus 1 multiplied to x. Now, this is exactly what we needed to show. This is the statement P of m plus 1. We have to show that 1 plus x raised to the power of m plus 1 is greater than or equals to 1 plus m plus 1 times x, the statement number 3. Actually, this is actually statement number, let's call it 3.1. Just to avoid confusion here. So here we have used statement 3.1 and 4. So we were able to successfully show that this is indeed a true statement because this inequality holds. So this simply implies that P of m plus 1 is true. So what we were able to do here is we were able to show that thus, if we say that P of m is true, if the statement P of m is true, this simply implies that the statement P of m plus 1, that also becomes true. That also becomes automatically true. So that means if we pick up any integer value m, then it's true that the statement becomes true for the consecutive integer as well as consecutive integer as well. So we can generalize this, and finally we can say that the original statement P of n, this is going to be a true statement. This is going to be true for all n belonging to the set of integers. Okay, and it's going to be positive integers.